Okay, so last time we left off, and we were talking about basically this set of numbers. We can only represent computer numbers on a computer in a set of discrete numbers. And if we have a number that's not one of those discrete numbers, it's going to fall in the gap between two of those numbers that we can actually represent. So in general, we're going to be able to. This is the fact that we can't work precisely with numbers on a computer is not going to be a huge problem. In part because there are lots of tricks for getting around it, and you're already starting to see some of these. You saw, using the log on the problem set. We're going to see some other tricks. It is possible, although oftentimes you don't need to do this, to actually work with higher precision numbers. And basically, in part, the way that you do that is you store the numbers with more than 64 bits. You can then assign more digits, more base 2 digits, more bits to the part of the number that's the D. That's the D part that accounts for the precision. So if you do need to do stuff in higher precision, one piece of software that lets you do that pretty easily is Mathematica. So you can work with Mathematica. There's also a package in R that will allow you to do some of this. So here's a little bit of an example of that. So it's this RMPFR package, which I, for some reason, cannot type the MPFR in the right order. But once you're actually able to type it, it will work. So here's what we can do with it. So if you ask for help on MPFR, it'll say, okay, what's the number you're interested in working with? And you can give that as a character vector, so your character string, so you can type in basically the number in as many digits as you'd like to. And then it says, okay, how many bits do you want to use to represent the number? And then what base do you want to work in? So instead of using 53, which is going to be the default, which is what we have when we're using double precision floating points, you can use a larger number of bits. So as an example, here's what happens if we represent pi with more than the 64 bits, the 53 bits for the precision part of it, and we can indeed write it out in all its gory detail here. If we wanted to look at some of the kinds of numbers we were looking at before, so for example, if we use 40 bits to represent 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, well, that's not as many as 53 bits, so we're not going to do as well as we do when we're actually just using R's regular double precision floating point, the computer's underlying regular double precision floating points. Okay, so we lose some digits here that we would have in our normal representation. But if we start to go above 53 bits, then we can actually represent the number with more precision. So here you see, okay, we've got out to 8, we've got out here to the second 8, and then we've got a whole bunch more 9s, indicating we've got more precision in representing the number. Because the actual number is of course, 8 with a whole bunch of zeros after that. And I could, continue this ad infinitum and see what happens when I use 600. It looks like it's just sort of cutting things off and saying that's essentially exactly that. I don't know. I think that might mean that it's actually able to represent it in 600 bits precisely. I guess I'd have to think about that a little bit more. So if we really did want to say do this subtraction, where we've already seen that we are not able to do this subtraction because we can't represent these values down here in our usual double precision floating point. So if we just do this in R, as we've already seen, we're going to end up with 0 as the answer instead of 1 times 10 to the minus 16, 17, 18. 1 times 10 to the minus 20 is the actual answer. But if we did this using these MPFR higher precision representations, then we should be able to get the right answer. So I'm going to use 100 bits in this case. And if I do that, it looks like, okay, I indeed get the answer 1 times 10 to the minus 20 after rounding with some reasonable, because of this is how the 100 bits of binary precision translate into precision in terms of the decimal base 10 number. Okay, so any questions about that? Okay, so let's now turn to what some of the implications are of this fact that we can't represent numbers precisely on a computer in terms of both doing calculations and in terms of doing comparisons, which was what I'd asked you to look at for a few minutes. over the 2 days since we last met. Okay, so one of the things is that all of our usual mathematical rules, going back to, whatever this was, when we were 10 and we were learning about arithmetic, all of these rules don't actually hold when we're actually doing things on a computer. So I can, if we think about associative and distributive laws and things like that, the order in which we do the calculations matters because whenever we do any single calculation, in most cases we're going to lose some precision, and that's going to have a different effect depending on what ordering we do the calculations in, as in terms of how it plays out. So, oops, wrong one. Okay, so what I'm going to do here is I'm just going to create 3 decimal numbers, and I'm going to multiply them in different orders. I'm going to do 1 times 2 times 3 and 3 times 2 times 1. And if I ask if these are identical, it says, nope, they're not the same. Even though I just took 3 numbers and multiplied them just in different order. And if I look at res 1, that's the answer as far as we can see. If I look at res 2, it's not very different, but it's enough different, that we don't actually get precisely the same number in terms of the extent to which we can represent it. So this is, these are differing in basically probably in the 16th decimal place here. But that's enough then that R says, oh, these aren't identical numbers. Okay, so don't expect, basically don't expect infinite precision whenever you're working on a computer in any of these current sorts of calculations. Okay, so in terms of comparisons, it came up last time when we started to say a little bit about it, but we didn't sort of flesh that out completely. What are the implications for when we're doing comparisons and saying, is A equal to B, is A bigger than B, is A less than B, is A greater than or equal to B, et cetera, et cetera, et cetera. Okay, so I asked you guys to think about a few. I think these are more or less the ones that I gave you to think about when we were for thinking about in advance of class today. So we've already seen this one, right? We've seen that if we subtract this and then say, is this equal to 0.1, and just enter 0.1 on the machine, we've seen that evaluates to false. Right? So that's just our standard sort of issue with dealing with floating points. So what about this? If I say, is this equal to 1, is that a safe thing to do in this particular case? Okay, so why is it safe? Okay, so they're integers. We, as you're going to see on the problem from the next problem set, but as we already talked about, we can represent integers precisely in base 2 up to some largest value, which is 2 to the 53rd. This is obviously a lot less than 2 to the 53rd, so we can represent both of these guys precisely, and so therefore we're going to be able to get a precise answer from doing the subtraction that it's 1, and then if we evaluate whether that's equal to 1, we're going to get true. So this will be okay. What about this guy? Any difference between that and the 0.3 minus 0.2 that you can see? Okay, so that's presumably something very similar to this one that we probably are not going to get the exact answer there. So let's actually see. Okay, so that's false. I can monkey around. That actually doesn't make any difference in terms of R's representation. But so indeed, that doesn't work for the same reason that this doesn't work. Is this going to work? It did, okay. So you tried it and it worked. Before we get to whether it actually did work, would you think that it would work? Okay, so we wouldn't think that it would work for the same reason we wouldn't think that this one would work, right? Okay, so we think sort of in principle, and if we're sort of just doing this as a general rule in terms of whether we want to be relying on calculations like this, well, that's not that much different than this. So unless we came up with some very strong reason for why this is safe and this isn't, it'd be hard to sort of use the fact that this worked and rely on that when we're actually doing any calculation. So in some sense, we probably don't want to rely on this working, even though it did actually work for this specific case. Did anybody get a sense for why this? Did everybody sort of think about this a little more and get a sense for why that actually did work? Yeah, yeah.
So because 45 and 44, if you represent them in the base 2, they have the same length. So they are going to give 0.1 the same number of digits, and that will lead to the same number.
I think I'm not quite following you. Can you?
The reason, let's say 4 and 4.1, 3.1 doesn't work because 3 is 1, 1, and 4 is 1, 0, 0.
Okay.
Yeah, so then the number of digits that for 0.1 is less for 4.1. Because in total you have like 52 digits.
Well, so 4 would be
1, 0,
1, 0, 0 in base 2. Is that what you're saying?
Yeah.
Okay. And then 3 would be
1, 1.
Wait, that can't be right. So 3 is 2 to the 0 plus 2 to the 1. So you're saying it's 0 point. Wait, how do I do this in base 2?
4 is 100.
Oh, right. Okay, that's what I was getting right. So 4 is 100, and 3 is 0, 1, 1.
Yeah.
Okay, so we could do that subtraction exactly.
Yeah, so like say in 4.1 you already used 4 digits for 4, so there will be only like 48 digits, 49 digits for 0.1.
Oh, I see. So you're thinking about sort of how many digits are used for the different parts of the number.
Yeah.
Right, well, if we think about the 0.1 part of this, that would then start to change what the digits are back here in both cases, right? So I think you're sort of partly onto it, that once we include the 0.1, that's going to change these digits, and then we're going to subtract things, and as a result of representing both of these numbers, then these digits out here are going to be different. Any more thoughts on what's going on that's different about this? Yeah, Tom?
I just thought that since each individual number in this case can be represented exactly by base 2 numbers, then the subtraction.
Right, but we can't, what do you mean by each individual number? Each of these?
Yeah, I mean, I would just assume that they're both probably represented exactly by.
Okay, so let's test that. So that's actually not the case. So if we look at it, we can see that 45.1 is actually represented not precisely. But let's actually now look at 44.1, see if anything jumps to the fore here. So it's sort of interesting. We look at this and we see that, actually it seems like it's being represented back here in the same fashion. So neither of these is exact, but the sort of the representation that's being used on the computer is such that if we do subtract them, we're going to get back just 1 from this position. So I think what's going on here is if we think about the base 2 representation of this, when we get 45 and 44, I think what's happening is if you represent those in base 2, basically you're using digits out here to represent the 45 and the 44 part. And then for the 0.1, if you look at the base 2 representation, you end up using digits over here. Those two digits sort of don't overlap and affect each other. And you have enough sort of space in between them that you can basically subtract these two parts and get back the 1 as if you were representing it as an integer, as if you were just working with the integer. And then you have the imprecise representation of 0.1 that's the same in both cases in this part of the base 2 representation. And so when you subtract that part, it actually cancels. So I think that's basically what's going on. And if we represented these things in base 2, I think that's what we would see. So in some sense, we're sort of getting lucky here. I mean, it's not really luck, but we're sort of getting lucky here in terms of the cancellation, even though neither of these two numbers is getting represented actually precisely. So it's sort of an interesting case. You get these sorts of things that you might not expect happening. But as I was sort of saying before, we wouldn't want to rely on that because you'd have to sort of figure out exactly what are the rules such that this works and this doesn't, and you wouldn't even want to sort of generally rely on this sort of calculation working. So what about this one? We take this very long number that ends in 5, 6, 7, 8, and we subtract this essentially the same number but ends in 5, 6, 7, 7. Is that going to work? We're going to have some people nodding. So this number only has 16, we're trying to represent 16 digits, so that should work. just barely. That should work. So we should be able to represent this number in base 2 exactly. We could look at 2 to the 53rd and see is this number indeed less than 2 to the 53rd, and what we should see is that it is less than it. So we should be able to represent both of these precisely. When we subtract them, we should be able to get 1 precisely, so that should work. But now if we go to this is now 16 digits plus 4 digits. This is 20 digits. This is beyond 2 to the 53rd. So it's beyond the largest integer that we can represent exactly, and it gets into the case where we're now skipping integers that we can represent precisely. So we saw last time that we could represent 2 to the 53rd, we can represent 2 to the 53rd plus 2, but we can't represent 2 to the 53rd plus 1. And then as we get further out into larger magnitude numbers, we start having to skip, we only can represent a number plus 4, a number plus 8, et cetera, et cetera. So this is going to be one of those cases where we're out of range. We're sort of bigger than 2 to the 53rd. We can't, we lose these digits when we represent them, and then when we subtract, we're not going to get back the correct answer. So that gives you some sense, I think, of sort of what of the kinds of evaluations that we could do that are going to be safe to do. And the other thing I'll point out is that it's still going to be safe if I just read in the data, say, from a character string, or if I just type the number into R and I say A equals 0.37 and B equals 0.37, that A equals B is still going to be true, because these are not, neither of them is represented precisely, but they're both going to be represented in the same way. So the question is whether, have I done some calculation to arrive at, have I done a calculation to arrive at this and a different calculation to arrive at this, or have I done a calculation to arrive at this and just given R this, in which case it's not going to be safe to do the comparison. So that it's sort of, in some ways, it depends on how you got to the numbers as to whether when some comparison is going to be safe to do. So Dustin, you had a question?
Do you know if there's a function in R that will take some number and then output like a vector of logical 1s and 0s to represent the binary of it?
So you can definitely do that in Mathematica, and I wonder if that's possible in here using this MPFR package. I guess if we, although I guess what's going to happen if we do this, so let's say use a lot of, no, not that many. If we say base 2, oh, okay, so yeah, I don't think this is sort of going in the other direction. Right, okay, so this is saying, it's expecting me to give it a number in base 2, and I give it a 4. It says, oh, that's not base, that can't possibly be in base 2, so try again. So yeah, I don't know off the top of my head if there is. I wouldn't be surprised if there is. It seems like the sort of thing that somebody might have written at some point. Other questions? Okay, so in R there is a, we could either, we could write our own function to calculate whether things are more or less equal, and that's going to try and respect the fact that we can only represent numbers with finite precision. So one of the sorts of things that you could do, a rule of thumb, is to say, okay, we're going to see, is the difference between the two numbers, so here I'm just building up a little function, is the difference between the two numbers less than machine epsilon times basically the magnitude of the numbers? Okay, so this is getting at this question of, okay, we know we've talked about the spacing between numbers as being the magnitude of the number x times machine epsilon. So here's machine epsilon here in R. Let's go ahead and do a comparison that makes use of our understanding of how numbers are represented and what the spacing between the numbers is. So if you are going to be doing checks of this sort, where you're actually checking numbers that that come about from calculation, then you're going to need to do an approximately equal check instead of an absolutely equal comparison. So that's the idea here. And if we so here I've got two numbers that they're actually very large magnitude numbers, but I run out of precision in terms of they're just integers. I run out of precision in terms of representing that 20th digit there. But if I say, are these things approximately equal, then my little function spits back that yes, they are approximately equal, because up to the precision with which we can work with them, they're fine. Okay, so yeah, and there is an R function, all.equal numeric, that I think does something very similar to that little function that I just concocted there and presented to you. Okay, so questions? All right, so let's talk a little bit more about what are the sorts of, so we've just talked about comparisons. Let's talk some about what sort of trouble can we get into in actually doing calculation. So the first one is one I basically have already mentioned, which is that if we have large numbers that are, well, basically if we have any two numbers that are more or less the same magnitude and we either subtract them or add a negative number and a positive number that are essentially of similar magnitude, the result is going to be that we're not going to have, the resulting number we're going to have is often going to have very little precision in the answer, basically because the digits of accuracy that we're using to represent the number basically cancel out when we do the subtraction, and all we're left with is basically the garbage amount at the end, the imprecise representation at the end that doesn't mean anything. So if we think about subtracting these two numbers, okay, I can represent all of these numbers, all of the digits here accurately. In fact, I can represent two more accurately. But as soon as I do the subtraction, all of this part is going to cancel with all of this part. So really all I'm doing is subtracting these two digits from these two, or these two digits from these two digits, and I've only got 4 digits of accuracy in the part of the number that hasn't already canceled out. So as a result of doing that, I'm going to get back a number that's not too inaccurate, 0.56, and basically 4 digits of accuracy here. But the fact is, I might have expected going into this, and if I didn't know something about this, that, well, I can represent 0.56, I can represent that to 16 digits of precision. Why can't I get a really accurate answer, 0.56000000 out to the 16th decimal place? Well, the problem is, as a result of the fact that I did the calculation that I did here, I can only represent it out to a few digits. Okay, so that's catastrophic cancellation. The same thing happens with smaller numbers. If I think about doing this subtraction here, again, if I just did this in my head and I said, okay, what's the answer to this? This is many, many zeros, 1, 2, 3, 4. I should be able to represent that as basically 1.234 times 10 to the minus 20 or whatever, and I should be able to have 16 digits of precision in that number. And therefore 16 plus however many decimal places are accounted for in the base, I should be able to have 30 some odd decimal places of accuracy. But again, catastrophic cancellation is going to hit me here. I'm going to basically catastrophically cancel these 8 digits here, so the most I can expect is I'm going to have 8 digits of accuracy left after doing this calculation. And indeed, if I look at it here, if I count these out, it looks like I'm right around 8 digits of accuracy, and then things fall apart once I'm out to here. So regardless of the size of the number, this sort of cancellation can happen. Okay, the next, actually before I do that, let me show you this example of how things could go wrong if we did a calculation naively. So again, this is sort of in the vein of things can go badly wrong if you don't know what you're doing and you're not careful and you sort of proceed ahead naively, but there are often fairly simple fixes so that we can actually do the calculation we want to, and it's actually not very hard to deal with. So suppose I'm doing a sum of squares, and suppose I'm just sort of proceeding ahead and you say, okay, mathematically I could compute a sum of squares. I can either compute it as a number minus the mean and then square and then sum, or I compute it as the sum of the squares of the x's minus, the sum of the mean of the x bar squared, and then n times that. So the problem is that once I start to do it this way, I'm starting to work with very large numbers. So if we actually look at this in terms of actually trying it, okay, so I'm going to take some x's. I'm going to make them to be very large, or moderately large. So I'm going to try and do the sum of squares calculation with these numbers, which are big but not not huge. And so if I just do that and actually do the naive calculation where I try and square them, and then do the subtraction, I'm going to run into trouble. And the answer I'm going to get back is 0, which is obviously not the sum of squares of these numbers. So you could play around and see exactly what goes wrong in terms of the numbers getting too big, and then if I try and subtract them, I don't have any digits of precision left, and you could work through exactly how that works out in terms of the sorts of concepts that we've been already talking about. But the main point I want to make here is that all we have to do to fix this problem, as long as we recognize what's going on, as long as this is not, this calculation could be hidden deep inside your code somewhere. You don't actually go and see that, when you calculate this, you get a nonsensical 0 as the answer, and you proceed ahead, and your calculation, has a bug in it. On the other hand, all we have to do is take x, subtract off its mean. That's going to get rid of this, this common value of 1 times 10 to the 8th. That's basically the magnitude of all of these numbers, and then I'm going to get back down to these numbers, which I can then do the sum of squares on, easily. So basically, subtracting off large values that are, subtracting off means of vectors is often a good thing to do in this kind of context. So indeed, if I do that, I get back exactly what the answer is.
What if I use the built-in SD function?
Yeah, so I mean, in general, anybody who's written code that's any good at all will know about these sorts of issues and will have accounted for those sorts of things in doing those calculations. So presumably that, I'd be pretty worried if that didn't work. So yeah, so it didn't give me 0. So it's it's doing the normalization here and taking the square root. So it's not giving exactly the same number, but that should be the accurate number. Okay. Let's see. So that was that there's a quick fix in a lot of these cases. So second thing that can happen with calculations, we've sort of already seen already as well, that if we take two numbers that are very different in magnitude and we try and add and subtract them, we're not going to have enough accuracy in terms of representing the larger number such that when we then either add or subtract the smaller number from it, we can have any impact on the larger number. So we already saw that with machine epsilon. If we take 1 and we try and add 1 times 10 to the minus 17 to it, we just get back 1, because 1 is too large. The relative magnitudes of those two numbers is too different. The 1 is too much bigger than 1 times 10 to the minus 17. Same thing if we do some sort of calculation like this. If I subtract that number, which is that so much smaller than this number, I'm going to get back just the original number because of the fact that I don't have enough, because of the disparity in magnitude of the two numbers and the limited precision with I can represent, with which I can, in this case, with which I can represent the larger one. So there's one of the things I want to mention here, and you'll play this out some more on the problem set, is think about doing this calculation. Suppose I'm going to sum up of a very large number of numbers. And I've got the number 1, and I add 1 times 10 to the minus 18th to it. We've already seen this is just going to give me back 1. Right? So now suppose I've got a quadrillion or an infinite number of these guys that I just keep adding to 1. Eventually if I add up enough of these numbers without adding them to 1, I'm going to get, or if I just, mathematically speaking, if I add up enough copies of these numbers, I'm going to get to a non-negligible number, and I should get an answer that starts to affect the 1. But if I add 1 plus this, and then I just keep doing that, this is just going to give me 1. I add on another 1 times 10 to the minus 18. That's also just going to give me a 1. I'm never going to get anything different than a 1, no matter how many of these I add on in this fashion here. So the order in which you do turns out the order in which you do the summation can matter, and that's what you're going to explore in the problem set. Okay, so that was so the catastrophic cancellation in this business with working with numbers that are very different in magnitude basically goes back to this question of how much precision do we have in terms of representing numbers. The other aspect of this is the fact that because we have a limited range of numbers that we can, because we have a limited range in terms of how big and how large, how big or how small a number we can actually work with, we can run into problems like that. You've already seen that in the problem set with doing that log likelihood calculation. So basically, anytime you see calculations that look like this, where you're taking products of numbers that could get very big or very small, you're going to run into the danger that you multiply a whole bunch of these together and you get something bigger than 1 times 10 to the 308th. That's going to be an overflow. Or if these are less than 1, if you multiply enough of them together, you're going to get something that's smaller than 1 times 10 to the minus 308. And all of a sudden your calculation is going to stop and you're not going to be able to get the right answer. So basically the rule of thumb here, again, is oftentimes a fairly simple one. If you see a calculation like this, think logs. Right away think about using logs whenever you see a product. And so if you work on the log scale, and either this calculation or this calculation together is going to work. You can do this. In this case, you may be able to exponentiate back to the original scale because you're going to get some cancellation here. And as long as you do it on the log scale and do the subtraction instead of trying to do it as division, you're going to be able to actually get back the right answer. In other cases, you may need to keep the calculation on the log scale and just say, this is the result I got on the log scale. Okay, so any questions so far? All right, so what I want to do next is do a little problem and see if you guys can work through and see what the trick would be to actually be able to do this calculation, and that will basically finish off the unit. Okay, so this is a calculation that comes up reasonably regularly if you're doing Bayesian calculations. So many of you have hopefully been exposed to Bayesian statistics, but even if you haven't, that's okay, because this is just an example that will get us to trying to do the numerical calculation that is at the core of this. So what this is this is basically a prediction problem. I'm trying to get the density of some new observation given data that I've observed and some covariance x. Okay, so this is just you can just think of this as prediction. I have some new x. I want to get the prediction for y star for that new x, and I want to calculate the density of that new y star. So in a Bayesian context, one way to do this calculation is if you have, this is the posterior density for some unknown parameters here, given the data and given the covariance, and then this is the predicted distribution of this new y, given the data, the covariance, and the unknown parameters. And in a Bayesian calculation, you may actually have a sample of values from the posterior distribution. So those are these theta j's. So the result is you can approximate this integral as a Monte Carlo average. We're going to talk about Monte Carlo averages in the simulation unit. 1 over some large number of samples m. This should be a capital M, sorry. Of a sum of, and now what I'm doing is I'm taking this term here. Basically, this summation replaces this actual posterior density. And this predicted density here, suppose that I have multiple values for which I want to do prediction. So actually so y star is actually a vector. Y, x, theta. And if these guys are conditionally independent of each other, then I can just write this out as, say, j equals 1, 2, however many of them I have, say n, y star j, sorry, that's I, y star I, okay, so I'm just gonna represent the density of a vector as the product because I'm saying that in this case I'm assuming these guys are independent. So now I've got a sum here that comes from doing the Monte Carlo average. I have a product here that comes from representing the density of a vector as the product of individual densities for the individual yi stars. And now I need to think about, well, how am I going to go about doing this calculation? Well, my first rule of thumb from what we just said before is if I see a product, think logs, because what's going to happen here? If we think about what a density often looks like in terms of numerical values, often if you just go ahead and say calculate a normal density, maybe you'll get a number like 0.02. So this is, say, f of y1 star. If I get enough of these, I'm going to get, so this is, say, so let's just make this easy. So this is 1 times 10 to the minus 2. It doesn't take very many of these guys to get to less than 1 times 10 to the minus 308. Okay. So let's say I had 400 of these or so, or 500 of these. you know, the result is I'm going to have 1 times 10 to the minus 400. This is already a number that's smaller than I can represent on the machine. Okay, so the result is, suppose that, suppose I try and do this product, well, let's see, suppose that how do I want to phrase this? Okay, so I can't actually do this product naively, because the result is I'm going to get an underflow. I'm going to get a number that's less than 1 times 10 to the minus 308. So, okay, so let's solve that problem with our rule from up there. Let's represent this on the log scale. Okay, so I'm going to just okay, so I have a product. Instead, I'm going to do that as exp of the log of that product. That log of the product I can, of course, represent as the sum of the logs. So that's how I'm going from here to here. So now I've got the exp here, and I've got the log here. Okay. So that's going to solve, just like in the problem you did in the problem set, that's going to solve the problem of can I evaluate this product? Except in this case, instead of getting numbers that are too big and lead to an overflow, I have numbers that are, in many cases, with a likelihood are going to be too small and lead to an underflow. So I can do this calculation. And let's say I get back a number like minus 400 or minus 500. Okay. So now I've sort of reduced this down to this calculation here. I have 1 over m sum j equals 1 to m of e, and I'm going to call whatever those numbers were Vj. So suppose Vj, the numbers Vj are things like minus 400, minus 405, minus 410, etc. So now what's the problem? If I now need to do the, I now want to do the sum, well, I have to exponentiate these numbers, but I already know that I can't exponentiate that number and still represent it on the machine, because I'm going to be, I've already said I have an underflow. This is less than minus 308, which is our lower bound. So I can't exponentiate this to do the sum, so I'm stuck. All right, so that's the setting, and I think that what I'd like you to do is take a few minutes and stare at this, and actually, why don't you find somebody else to talk it through with and see if 2 minds are better than 1 in terms of seeing if you see what the trick is to do this. So first, make sure that you understand what's, in talking to the person that you pair up with, make sure you sort of see what the issue here is, and if you have questions about it, try and see if talking together will help. And then what I'd like you to do is see if you can figure out a trick that you could use to actually compute this quantity here. And computing instead the log of this quantity is perfectly fine if you can figure out a way to do that. Okay, so just to reinforce this idea that we can't do that original calculation of the product, say this is the log likelihood. Say I have 300 observations. I try and do 0.02 times 0.02 times 0.02. You know, suppose all the likelihood terms are right around 0.02. I get 0. Okay, so this is the underflow. If I do it on the log scale, I can do 300, the number of observations, times the log likelihood, and I can get a perfectly legitimate log likelihood. Okay, so were there questions as people were talking about it, sort of not having questions about what the setup of the problem was or the context and what was going wrong? Okay. Any things that people came up with of how they might do this? Tom?
I just thought, looking at what you have there might be a possible way to manipulate it to where you can approximate that by taking the sum of the logs somehow instead of logging the sum, maybe?
Okay.
Because even if you take the log outside that sum, well, so the issue I see is that the BIJs are so small that e to the BIJ is close to 0.
Right. Yeah, so basically I'm doing, what I'm trying to do, and it might help to see the trick if we sort of write this out just as like a little toy example. Suppose that what I'm trying to do is e to the minus 400 plus e to the minus 401 plus e to the minus 398 plus e to the minus 405. Those are the sorts of numbers I'm trying to add together.
Yeah, so I mean, the numbers are similar. You can just pull out e to the minus 400.
Okay.
And then that way some okay number to calculate.
Right, so that's basically the trick of, in this case, the idea would be, what's the maximum of these exponents here? Okay, so let's just do it for this specific example. That's 398 in this case. Let me factor out e to the minus 398 out of each of these. Now I've got e to the minus 2 plus e to the minus 3 plus e to the 0 plus e to the minus 7, so on and so forth. Okay. Not quite out of the woods yet because I still can't do this calculation, right? But, well, what was this embedded in? Well, this was embedded in 1 over m log. If I do it on the log scale, this was embedded in that. Again, we're saying, we're using logs twice here. We've already used the log scale once. We're now using it again. Okay, so now I can do this as log of 1 over the m plus log of e to the minus 398, so that's just minus 398, plus log of this term. And I can certainly do this calculation. I'm not going to have any problems there because these numbers are not so small. So I can actually get this result in terms of, so I'm going to get, well, if we ignore that part, I'm going to get the minus 398. I'm going to get the maximum value that comes out of here, plus the log of the sum of the e to the vj's minus the max of the vj's. So this is the max of the vj here if we write it out more formally. So that's basically the trick. So I think part of the lesson here is, well, we've already seen, one of the lessons is just, use logs, work on the log scale. And the other is if you sort of stare at these things and sort of try to play around with them and manipulate them, oftentimes you can come up with a trick that allows you to sort of rearrange the calculation in a clever way. And that's what the idea was here. Okay, questions or comments there? Okay, so the last thing I'm going to do is just show you an example that's going to be a little bit of a precursor to where we're going in terms of some of the stuff we're going to talk about in terms of linear algebra. So I'm going to create a matrix which is a correlation matrix. And this is based on having an exponentially negative, the correlation as a function of lags in time being, the correlation being a decreasing exponential function of the lag in time between any 2 points, sort of like the example we've already seen. But the point I want to make here is this matrix core map that I create is a covariance matrix. It's a positive definite matrix. As we're going to talk about in the next unit, it mathematically has eigenvalues that are all positive. Okay. But if we actually look at, and in R compute the eigenvalues using the eigenfunction, which we're going to see quite a bit of in the linear algebra unit, and if I look at the last 20 eigenvalues, what I see is they're all negative. Okay, so even though mathematically I know this matrix has all positive eigenvalues, if I actually look at the 20 smallest eigenvalues, I see that they're all negative. But you'll also notice something interesting, which should start to, lead us to understanding what's going on. They're all right around 10 to the minus 16. Okay, so this has something to do with the fact that we don't have infinite precision in terms of representing numbers, and as a result, these eigenvalues are all actually slightly positive and very close to 0, but numerically we can't actually do the calculation precisely, and the result that we get is it looks like it's a negative, it's not a positive definite matrix, even though mathematically we can prove that it is a positive definite matrix. Okay, so that's just, I'm not going to explain any of that here. We're not going to talk about the eigendecomposition quite yet, although we will on Monday. But I just wanted to point out that all of this stuff comes up when we're thinking about linear algebra as well. So let me just switch for a couple minutes to the linear algebra unit, give a little bit of a preface here, and then we'll start in on this in detail on Monday. So the first thing is, I said in a Piazza post that what I want you to do is look at subsections 1.1, 1.2, up through 1.8, and make sure you're familiar with that material. It's basically just background of linear algebra that I'm expecting that you know coming in. So if you haven't done any linear algebra in a long time and that stuff doesn't look familiar to you, look through it, go review your old notes. Feel free to come in and talk in office hour to me or to Tessa, because I'm going to assume that you know this coming in. The other points I want to make here are just sort of the key principles starting out as we're thinking about doing linear algebra, which is the way we write a linear algebra calculation mathematically is not in many cases going to be how we actually carry it out on a computer. So if we're actually doing this calculation on a computer, we do not actually create x transpose x and then calculate its inverse and then multiply the inverse of that matrix times x, or times x transpose, and then multiply it by y. We have to think much more carefully about, what's the order in which we do things and what is the actual way in which we do the calculation, such that we can both speed up the calculation quite a bit and also in some cases so that we can make sure we have a reasonable amount of precision in our answer. And if we do it naively, we're going to do it much more slowly than we need to do, and in some cases we're going to do it with very little precision. Another example here is if I think about doing, oftentimes in many calculations we might end up working with a permutation matrix, which is just going to reorder rows and columns of a matrix. So mathematically I can write out a permutation operation as a matrix P which has a bunch of 1s and 0s in it. And so if I were to try and take A times B and then permute rows of the matrix, I might do it by writing it out mathematically like this. And that's fine to write if you're thinking about it mathematically. But if I think about actually doing this calculation on a computer, I don't actually need to multiply this times this to do the permutation. Right? I can think about the fact that when I go to multiply A and B, well, what does the permutation say? It says just switch around the rows of A. Well, as I'm writing for loop, if I'm writing C code to do for loops to do this multiplication, I can just, instead of going to the first row, if the permutation says go to the third row, I can just go to the third row. I don't need to actually do the permutation initially before I've done this calculation. Okay, so I'll stop there and we'll pick up with this on Monday. Hey, let me just close this out.